Okay. Hi, everybody. Welcome to AP Chemistry for the day. The date is, no, I'm kidding. Number 4, calculations where K is already known, working backwards. So, K for the reaction below has a value of 55. Remember, no units. This may make 0 sense to you for a little bit, Allison, but that's okay. At a certain given temperature, calculate the number of moles of HBr present in an equilibrium mixture that contains 3 moles of hydrogen gas and 0.45 moles of bromine vapor at this temperature. What's our first step going to be? Write the K expression.
Oh, I got you guys.
Okay.
So write your K expression. Try to do it without looking up here. I'm doing my work, you do your work.
Bless you.
Did you remember, number 1, products over reactants?
Yes.
Did you square it?
Yes.
You have to remember that the coefficient becomes the exponent. Yes? That should say HBr. Better? There we go. Got it. HBr. Okay, step 2. Let's sum in what we know. So K is 55 is equal to, we're just going to make this x squared over 3 times what?
0.45.
Yeah. 3 times 0.45. Solve for x. Easy. Solve for x. X is a real number. No quadratic formula needed on this one. This next picture did not print very well, so we're going to have to do some labeling, I think.
Vibes.
I had 8.62 moles. Yes?
Yeah.
So we're going to do, if it's sig digs, I guess it'd be 8.6, but we'll just do 8.62 moles of
HBr.
HBr. So you can work backwards to an individual number of moles or concentration as well. This is really, really important, this next part. The magnitude. The magnitude of K can give a quantitative guide, all right? A quanta, Q-U-N-T-I?
Yes.
Q-U-N-T-I,
T-I.
quantitative guide. There's an N right here.
Oh, okay.
Yeah. Quantitative guide to the amounts of products and reactants present at equilibrium. We talked about this a little bit yesterday. Present at equilibrium. Very large K values indicates large numbers of products. Large numbers of products. And reactions that basically go to completion. Very small K values indicate large numbers of reactants. And reactions that hardly proceed at all. This will be very important later. That's going to be so important to us. Especially small Ks are going to save your math life. So maybe you could think about what we did yesterday and how that could help, all right? Maybe not, but you'll see why. So we're going to have to do some labeling over here. So because you can't, this is supposed to be in color, so I have HI, this is 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 HI, let's just, this is HI, this is HI, and this one is HI. The ones I want to circle are well, it's kind of weird. This one is H2.
Right.
This one is I2. This one is H2. And this one is I2. That should have been in color. It would have been a lot better, but it's not in color. So, take a look at the diagram. We have a lot.
There's one left.
Oh, shoot. That's
Wow.
HI.
Okay.
That's HI. So, you got this all labeled now. What can be said about the equilibrium position in terms of reactants and products, the likely magnitude of K, and the extent to which the reaction proceeds? So let's start about what do we have a large amount of? We have a large amount of HI, which is products, right? So that means that equilibrium, right? Equilibrium is going to, we'll say equilibrium lies to the which direction?
Right.
Right/forward. That means it's favored forward. The reaction is favored to go forward. So K equals what? Big. So K equals big.
Well, that's a big.
That's a big, yes.
Is there a reason for that? Or is it just big?
It's a big.
Okay.
Big.
Yeah.
Because I have a small big, but I still get the same message.
As long as you get the same message, I'm good with it.
Okay.
Flip it.
It's dangerous.
Yes.
You want to be
How do
unequivocal.
you know it's big?
Because it's products over reactants, right? So if I have a huge amount of products, the top of that fraction is going to be big. That's all we're talking about is products over reactants. Okay. So this can be done for gases as well. Is it GASES?
Yes.
For gases too. So
Ice.
if I'm talking about the partial pressure of A, this would be, there's an equation, it's the mole fraction. Don't worry about that. It's the mole fraction of A times the total pressure. So the mole fraction is just a new little equation. So this says mole fraction of A times total pressure, just in case you can't read that. To get a mole fraction, you take your moles of A divided by the total moles in the problem. So a mole fraction is just the mole of one individual thing divided by total moles. Will you see that on the AP test? Probably not, but I just want to throw it out there. So now it's asking for Kp, also known as just the K for pressure, right? So what would Kp be for this equation? Well, Kp, would be the concentration of,
C to the C.
it would be Pp, partial pressure. Sorry guys, just stick with me. Pp big C to the little c times partial pressure, I'm just going to say partial pressure, of capital D to lowercase d.
Wait, was it big C to the little c?
Yeah, it's big C to little c, right?
Someone needs to make more of a distinction
Yeah.
between those letters.
Isn't it shame for letters?
I will fix that for next year.
The English alphabet. Please.
Over the partial pressure of A to the little a over the partial pressure of B to the little b.
Huge.
Essentially, it's the same thing as what we did yesterday.
What I saw online when trying to understand this is for the uppercase C, they put a line through the middle, so you know it's upper.
Oh,
Z.
that could work.
Yeah.
It looks
Then
like
you have euros.
it's like for the if you did for the uppercase B and put two lines, it would be Bitcoin then. Yeah.
See, this just becomes currency. It's
Yeah.
not things.
However you want to do it is fine. You're not going to be writing equations like this, right? This is just a form, all right?
There's no way.
This is just a form. You're going to be writing stuff with real things, right? So you don't have to worry about that. So, what would Kp be for the following? So, the first thing, don't write that yet. I just want to Google something really quick. Partial pressure equilibrium, and make sure I'm drawing this right. because this was something that was a little bit surprising when I was at the AP grading last year. Yeah, that's what I thought. Okay. So, whenever you are doing pressures, I just remembered this, okay? Whenever you are doing pressures in equilibrium, you do not actually put it in brackets like I did, okay? You actually put it in parentheses, all right? So you have to think, what? Brackets is a concentration, but pressure is parentheses. So think, pressure, parentheses, pressure, parentheses, pressure, parentheses. And they actually took off for that. I had a question I graded, and I was shocked that people did all the math correctly. They had their stuff in brackets, and they took off a point for that.
Boo.
Because they said that a gas can't have a concentration, which they're kind of right. So if you're ever doing equilibrium with pressures, it's got to be in parentheses. So this should have probably been parentheses. All right? I just remember that, and I'm really glad I did.
It's easy to accidentally write brackets under pressure.
Yeah. Okay. So KP is going to be parentheses. What?
FeO4.
Eh.
No. H2 to the fourth.
Why is Fe3O4 not in my K expression?
Solid.
It's a solid. Solids and liquids are not part of equilibrium. Is a solid going to affect the pressure of this? No. So it's going to be the the pressure of, so partial pressure of H2 to the fourth over the concentration of
H2O.
the partial pressure of H2O to the fourth. So that's what that would look like. So there was your first time. Yes?
Parentheses for gas, and then
You basically use parentheses for pressures. Pressure is parentheses. Everything else is brackets. So it'll be a whole problem in parentheses. Pressure is parentheses, everything else brackets. Okay. Now, when equilibrium has not been established, or I'm going to cross out these solids just so it's a little bit more emphasized there. Not been established or is in the process of being established, we must now use the reaction quotient, or Q, yes, there it is, to determine what extent the reaction has proceeded. So, if I was going to write a Q expression for this, guess what it's going to be? Same thing, right? It's going to be big C to the little c, then it's going to be big D to the little d. Wow, that looks like a D, a B. It's going to be big A to the little a, and it's going to be big B to the little b. I know it's repetitive, but I'm showing you it's the same thing.
In parentheses or brackets?
But it's Q. We're back to brackets because we're aqueous. So we're back to concentration of something. The only difference, yes?
like why is it the same thing but you're different letters?
What do you mean? I'm just saying the process.
Yeah, you're using the same formula though, so why do you end up with different values?
Here's why. So here we go. The only difference between Q and K is that K is when it's at equilibrium. So K is when equilibrium has been established, while Q is the same ratio at a different time. And we've already emphasized this a little bit, but this is usually before the reaction has started. So your Q values are going to be different than your K values. So Q is before the reaction started, K is when it's at equilibrium. So you're going to have a different number for this than this, almost all of the time. Here's how you compare them. If Q is greater than K, that means there's too many products. There's too many products in the reaction mixture, and the reaction will shift left/backwards. Because if there's too many products, which way is it going to want to, like, think about almost diffusion, right? If there's too much over here, it's going to shift the other side, yes? If there's too many products, it's going to shift back towards the reactants. Yes? I'm doing it from your view,
Yeah.
right? If I have a lot over here, it's going to want to shift the other way.
I thought big K.
K is just K.
K is just K. We're talking about Q now. We're comparing Q and K. So this is initial. Q is initial. K is at equilibrium. So if Q is bigger than K, right, it's going to shift left because that means I have too many products. If Q is less than K, there's too many what? Reactants. And I'm going to help give you a shortcut for this in a second. And the equilibrium is going to shift. Wait a second, I skipped a line. To the reactant side in order to produce the reactant, we're at lower. I'm sorry. So the equilibrium will shift left backwards, right? What is it going to shift to? So I have too many. It's going to shift back to what? Equilibrium, right?
Yeah.
It's going to shift back to when it's in equilibrium. And when it's at equilibrium, Q equals K. When it's at equilibrium. Now can somebody grab the door quick?
Oh, is this from the teacher Eric lesson?
I know, somebody with blonde hair. We're gonna know that he's talking to himself. That makes no sense. Yeah. A lot of stuff happened
Eric,
yesterday.
ask your
Also,
future self if we get a snow day tomorrow.
also,
She's
Jacob is gonna get hit by a bus.
Mayor wants to go to
A psychic. Yes.
Jake could be killed by a bus. But
Right.
I will be injured, but I will survive. I'm confident.
Okay.
It's gonna be really ironic.
You missed a lot of non-chemistry and chemistry yesterday. So, if Q is less than K, then there's too many products, so it's going to shift to the right/forward.
We meant reactants. We said that, right?
Yeah.
I think I did.
Okay.
Yeah, if there's too many reactants in the reaction mixture, yeah,
Yeah.
it's going to shift right/forward. Or to the product side, in order to increase the product to reactant ratio, where once again, Q would equal K. If Q already equals K, then it's already at equilibrium. If you think about this like a deck of cards, this is what I thought of a couple years ago. If the queen is less than the king, is that correct in a deck of cards?
Yeah.
Yes.
A queen is less than a king in a deck of cards. That is
I played games.
right.
I'm just not.
If I'm just talking about a deck of cards, all right? I'm talking about in a deck of cards, a queen has a lower value than a king, correct? That is correct. That is right. If the queen is greater than the king in a deck of cards, is that right? No, so that's left.
So it's not right.
And if Q equals K, it's at equilibrium. All right? Now we have achieved justice. All right? We have equity. All right? It's at equilibrium. But that really will help you remember it. All right? If you think of a deck of cards. So you're going to have a Q value, a K value, you're going to compare it. And you're going to know, is it going to shift to the right? Is it going to shift to the left? And here's the other thing. Remember yesterday how we were putting like 0 for the products, right? Well, if we compare our Q and K, oh, it's Mr. Miller.
She got snowballed.
It's because he's watching me, because he knows what my prediction is for tomorrow. He takes it very seriously when I mess up.
Okay.
Yeah.
So,
Yeah, I know.
So,
Because they're snowballs.
I know, there was one year he brought up, was that 8th graders? He brought his whole class down at me and threw snowballs at me when I was
Way to
wrong.
go. That was us.
Wait, you-
Inside.
But inside, yeah, paper snowballs.
Oh, like he made us make two each.
Paper.
And then
He's actually,
I thought he was real
Mr.
snowball.
Miller is a huge, he's a big trickster. He's all about pranks.
He literally made it sound like a project too. He was like, okay, go grab a piece of paper from the beginning. We're gonna start folding it, and then he goes, screw it, just crumple it up and
Yep.
follow me.
Anyways, so here's why this is important. Knowing which way it shifts tells you in your ice which way we're either adding x's or taking away x's. Yesterday we were just assuming it shifted to the right. Agreed?
Yeah.
But now once we have Q and K, maybe your plus x is going to be on the reactants, maybe your plus x is going to be on the products, but you'll have to do this first. Does that make sense?
Yes.
All right? That's why Q didn't make sense yesterday, okay? But it should make a little bit more sense now. If it still doesn't make sense, you'll see in a second. We're going to do an example. Flip it. It's okay. It'll make sense in a little bit. In a situation where two reactions occur with a common, what do we have here? A common what?
Okay.
Now think back to last chapter.
Denominator.
Intermediate.
Intermediate.
Oh.
You would agree that there's a common intermediate.
Something's formed in that form.
Something that's formed and gone that also has a very low concentration.
HC.
Right? Yes.
Facts.
It's possible to actually write a series of K expressions.
This is where I begin to lose it.
So if I was going to write K1,
You're losing it.
right? If I was going to write K1, K1 would equal what? Concentration of H plus times the concentration of HCO3 minus over the concentration of
H2.
H2CO3 minus. What would K2 be? K2 is going to be concentration of H plus times the concentration of CO3 2 minus over the concentration of HCO3 minus.
Wait, why is one of H2
Because, like,
minus?
Are we solving for HCO3?
What is the question?
Is it, for the first one, isn't H2CO3, isn't it not minus?
Oh yeah, you're right. There's no minus there. Gone. Okay. So my overall K expression is going to be K equals concentration of H plus squared times the concentration of CO3 2 minus over concentration of H2CO3.
Wait a second. Wait.
Yeah, you see it?
It's just the product.
You just multiply them together, right? All you do is you're multiplying K1 times K2. So when you have multiple steps, you can just multiply them together, or just look at the last step, either one, right? So K overall is just the product of K1 and K2.
Does this apply with more steps?
Yep, it works with however many steps there is.
This is lit.
But there has to be a common intermediate for that to work. Yes?
Okay.
Why would you do that if there's only one slow step?
I don't know. I'm just showing you.
Okay.
All right? I'm showing you multiple ways to do this. If there's only one slow step, right, then you know how to write it. But here, they're not telling us which one is the slow step.
Does the slow step have anything to do with equilibrium?
Not necessarily. Equilibrium is all about the final and what you're doing to it.
Then it doesn't matter if you slow that step
No.
3.
All about the Q equaling.
So, manipulations of K and Q. Here we go. So, here we go. Let's write the original K, the OG, K for this expression. What would it be?
NO2 squared over
Concentration of
partial pressure.
N. Oh, snap, you're right. Partial pressure, right? Because these are both gases of NO2 squared over partial pressure of N2O4.
Huge.
If the reaction is reversed, though,
You'll have to write partial
the
pressure.
new K, what?
You have to write.
So if we're writing parentheses, we don't have to actually write the PP anymore, all right? Because if you do the parentheses, it's assumed that's a gas. So are we okay not writing the PP anymore?
Yeah.
Because parentheses is pressure. So if I reverse it, my new K is going to be what?
N2O4.
Concentration of, I'm sorry, the pressure of N2O4 over the pressure of
NO2 squared.
NO2 squared. So the new Kc, if I reverse it, is what?
1 over.
1 over K OG. It's 1 over the original K. I'm just taking the inverse. If I reverse a reaction, it's just the inverse of the K expression. That's what I'm saying here. Okay? It's the inverse. If the equation is halved, my new K is going to be pressure of NO2 over pressure of N2O4 to the 1/2 power
To the 1/2. Oh, yeah.
to the 1/2. 1/2 is my coefficient, right? So I'm raising it to that power. So my new KC is going to be what for the KOG?
It's a square root.
Yeah, it's the square root of KOG. So if I have it, I take the square root of the original K. If I double it, my new K is going to be pressure of NO2 to the power of 4 over the pressure of N2O4 to the second. So what am I doing to my KOG?
Square.
I'm squaring it, right? If I tripled it, what would I do to my new K? It would be KOG to the third. So those are just easy manipulations of K. Helpful to know. You'll probably have, I think there's one problem like that in the problems, which there's a lot of problems in this chapter. There's a reason though. You've got to get this chapter.
So what is the test?
We'll have plenty of time
I
to
don't
work
know.
on it.
Not next week.
Okay, it's
Oh,
not next
oh.
week.
No.
Ooh. Then
I don't
that
think
is-
so at least. No, it's not.
He said he
Especially with
don't
the snow day
think so.
tomorrow.
Okay, let's.
Especially with the snow day
Usually
tomorrow.
with the
Yeah.
students.
Flip it. All right. This is huge.
Oh god.
What we're about to do.
Rich.
Le Chatelier's principle. Le Chatelier's principle. I've put a lot of stars here because this is super, super, super important. So this is some of the more qualitative / quantitative parts of equilibrium. But there's a lot of qualitative here. So this Le Chatelier's principle states when a stress, all right, do you ever have stress placed on you?
Never.
Yes.
Never. When stress is placed on you, what do you do in your 5-minute journal every night, Molly? You journal, right?
I do.
Because you're trying to get back to what?
When I'm stressed.
You're trying to get back to your equilibrium, right?
For sure.
So our equilibrium is like her mental health in this situation, right? So when we have a stress put on us, we try to de-stress, right? A lot of times the ways we have to de-stress is doing 25 homework problems, and then your stress goes down, then you take the test. Then it starts over. So no, I'm just kidding. All right? You actually don't de-stress until we're watching Back to the Future 1. Then we'll be de-stressed.
Yeah.
Anyways, when a stress is placed on a chemical equation or a system at equilibrium. So it's at equilibrium, and now I'm going to put a stress on it. There will be a shift in the position of the equilibrium to reduce that stress. So just like us, chemistry wants to do the same thing. It wants to reduce the stress. It's going to take the least restrictive path. It wants to do the easy thing. Easy way out. Just like you. All right? Just like Seth, who's never read a book.
Yeah.
Right? He took the least restrictive path. And look where it's got him. Still made it. All right? And how much of your AP Chem book have you read?
Ooh, I've done the homework.
Exactly.
Yeah.
So it's still working.
That's right.
It's still working. The shift
That could be the first book.
occurs because the stress will cause what to change?
Q.
Q.
Yes.
It's going to cause Q to change, and the equilibrium, still not enough space, sorry, has to shift to bring Q back into numerical agreement with what?
K.
There you go.
That's about me.
So, here are the types of shifts. Number 1, the addition or removal of products or reactants. Here's what happens. Let's put A, part A. It's going to shift to the other side if what? If something is added. It's going to shift to the other side if something is added. Think about it, right? Here's my reactants. Here's my products. It's going both ways, yes? If I add more reactants, what am I going to want to make more of? More products, yes? If I add more products, it's going to make more
React.
reactants. That makes sense, right?
Does K change in this situation?
Does K change? Is the temperature the same?
Yeah.
Then no.
Okay.
Only Q's changing. But you don't have to really worry about Q a lot of the times. It's just what's going to happen. Okay?
Okay.
So if you add reactants, it's going to shift to the which side?
Other side.
Forward or to the
Right.
Right.
right. You got it. If, so put B here. If something is removed, I've heard that every period today, I think, comma, it will shift to the side it was removed from. It will shift to the side it was removed from. Does that make sense? So I have reactants, right? And now I'm taking away reactants. Yes? If I take away reactants, I now have more products. So it's going to shift to that same side, right? So if I remove something, it shifts to the side it's removed from. If I remove products, I now have more reactants. It's going to shift to the products. Head nod if you're okay with that. All right, this is actually is not hard. You just have to kind of get it. That made no sense.
Just very like backhand.
This is not hard. You just have to get it. Guys, you just have to get it.
Just do it.
Change in pressure. When you change pressure, you're also changing technically, you can also change the volume to change pressure, right? So there's multiple ways to change pressure. By just adding something or changing the volume. Multiple ways to do that. So, let's do like this. When pressure is added, it will shift to the side where?
Opposite.
With the least number of moles of gas. If pressure is added, it's going to shift to the side with the lowest moles of gas. That's called what? Diffusion, right? If I'm adding in pressure, right, it's going to go to the side that has a lesser amount because that's where there's room. Is that okay?
You're adding in pressure in the form of one of the products of reactants.
I could just be adding just general pressure on the system.
Okay.
All right. Now, if I'm adding in like a reactant or product, that changes it. Okay. We're just talking about general pressure. Okay. I'm just talking about pressure. I'm talking about adding in maybe an inert gas or something like that.
Gotcha.
Okay. So I'm going to give you an example. If I have 2C solid plus O2 gas is in equilibrium with 2CO gas. 2CO gas. If I add pressure to this system, which way will it shift?
Left.
Yeah, it shifts left.
Because that's the least.
What's that?
Is the least.
Because it has the least moles of gas.
Which reduces the overall pressure back
Which-
downward.
Exactly.
That's
Yeah.
right. Okay.
It's just diffusion is all this is, right? Pressure wants to diffuse, right, to the lowest part. Yes.
Because if more of that reaction proceeds, then there's going to be more pressure.
You
from
got it. Yeah.
carbon monoxide to this code.
Right.
Okay.
Now, what if I would increase the volume of this same, if I increase the volume, which way is it going to shift?
Right.
Why? If I increase the volume, what am I doing?
Decreasing the pressure.
Increasing the volume is equal to lowering the pressure, right? Yeah, agreed?
Mhm.
Increased volume is the same as lowering pressure. And if I'm lowering pressure, it's going to shift to the side with the more moles. So that's still going to shift right. So pressure and volume are how related? Inverse. Boyle's law, right? So that's Boyle's law. Change in temperature. Change in temperature. This is the third way to stress the system. And 2 years ago, I came up with a new way to do this as well. It's super helpful if you do it like
Imagine you
this.
have a deck of cards.
Imagine a deck of cards. If it is exothermic, if the reaction is exothermic, which means it's what?
Delta H is negative.
Delta H is negative, right? Add heat, literal heat. So I'm putting heat in quotations. So you're literally going to add the word heat as a what?
React.
Product.
As a product, right? Because if it's exothermic, it's a negative delta H, but what does that actually produce? Heat. It releases heat. This makes it really helpful, all right? It's actually kind of genius. If it is endothermic, which is a what type of delta H?
Positive.
Positive. You're going to add heat as a what?
React.
As a reactant. Add heat as a reactant. So I'm going to give you an example. I don't know why I didn't give you more room to write, but I didn't. So that's on me. So I have FeCl3aq plus CaOH2 aq is in equilibrium with FeOH3aq plus CaCl2aq. Leave a spot. Actually, it doesn't really matter, but leave a spot here if you've got some room. And this is negative 36.3 kilojoules. Is that balanced? No, I've got 3 CLs. So this is going to have to be 2, 3, 3? 2, 3, 2, 3? Does that look better?
Yeah.
Okay. And I'm saying that this equation has a delta H of negative 36.3 kilojoules. Where am I going to add heat?
Product.
As a product. So I'm literally going to write plus heat. I literally write heat as a product. This helps me visualize it. This really helps me visualize it. So what would happen if I add FeCl3? Which way is it going to shift?
Right.
Shifts right. What happens if I remove CaOH2? How will that shift?
Left.
Jacob's answering really fast. Everyone else process here. All right, do you guys agree?
I'm on the first one, yeah.
Yeah, I'm still trying to.
So the first one, if I add FeCl3, FeCl3 is a reactant, right? So it's going to shift to the other side. Second was, I'm removing CaOH2. If I remove reactant, it's going to shift back to its own side. So it's going to shift to the left. And what if I increase the temperature? Pause, don't say anything out loud yet. Okay? If I increase the temperature, which way is this going to shift? Kale,
I don't know.
take a guess. You got 1 in 2 chance. I'm increasing temperature, which we wrote it as a what?
As a product. So shift left.
You got it. If I'm increasing the temperature, it's going to shift left because I'm adding in extra temperature, so it's going to shift back to the reactants. Got it? So that's why we literally write heat as a reactant or a product. That make sense?
Yeah.
It's super helpful. Super helpful.
I like it.
Because up until 2 years ago, it's just like visualize it, which is not great. All right? If you actually write in heat as a reactant or a product, it makes it really helpful. Increasing. I think I said something wrong 2 minutes ago, so forget what I said about an inert gas, okay? Forget that.
No.
Increasing total pressure by adding an inert gas
I already forgot.
actually has no effect on the partial pressure.
Wait, what's
That doesn't make sense, right? If I'm adding an inert gas, is that going to react?
What is it? No.
Inert is something that doesn't react, right?
Like helium.
So like helium, one of those noble gases,
The most reactive one.
right? This has no effect on the equilibrium. So you have to increase pressure by adding something else.
So it has to be one of the products or reactants?
It has to be something that's going to react. We're going to talk about the common ion effect coming up,
Well, I mean,
and that'll make more sense when we talk about that too.
can't affect the reaction.
Trey.
Would we ever add like another
Right.
compound?
I guess.
Yes,
Okay.
we will be adding other compounds into the mix.
Pressures
All right.
part of.
So eventually, where we're going to go with this is we're going to be adding in other compounds that have common ions. You'll have to figure out which side has the common ion. How is that going to shift it? There's a lot to go. All right. There's a lot to go. So you can see, here's a little example of what we just talked about. All right. So that's a little example of what we just talked about. And let's actually stop there for the day. Let's stop there for the day.
That is a good idea.
What?
Me personally,